Good morning, students. So today class will be seeing the concept of convolutional coding, and from that we will be seeing the concept of trellis and viterbi with the problem. So previous session, I'm sure we have seen the uh, concept of this uh, code tree. So I'm sure that you have understood about this concept, how this code tree has been designed. So we'll go for the next one is generalized code tree. So previously already we have found out the code tree. From that we are going to find out the generalized code tree. From that we are going to find out the trace the shortest route. Okay, trace the shortest route, and we have to find the message for that message bit. We want to trace the shortest route for the given message bit. So the given data, the given message sequence 1011. So that's the given sequence 1011. So MSB and the LSB is been given uh, most significant bit and least significant bit. I'm sure that you should have known this LSB and LSB region. So M0, M1, M2 are the shift registers. Initially, it will be 000, and if the LSB of the first bit is been given to M0, the M0 will be shifted to M1, M1 will be shifted to M2. Such a way it is mod load added, and two bits have been received like X1 and X2. Okay, so the encoded sequence can be taken in terms of X1 X2 as a combination. So let us take M0 M1 into a tabulation. Okay, a state M1 and M2 represent the state shift register, and M0 is the input message bit, and X1 X2 are the output sequence, encoded sequence. So we have seen this on the previous slide. So similarly to n minus 1, n is the number of shift register is 3, 3 minus 1 is 2 plus square is 4. So you have 4 states. Okay, this we have seen on the previous class, and what we are going to do is from this uh, encoded sequence we are going to frame a generalized code tree. Let us initially take 0, because at the initially shift registers will be 0 level. So you have this one thing you have to know here is uh, for the generalized code tree, two combinations, one at the input 0, one at the input 1. What happens? Okay, what is the output? So you from this the two different branch will be divided. Okay, so from one branch, two different branches will be divided. The topmost will be 0, the bottommost will be 1. Okay, 0 1. So two different input cases. What is his output? Okay, so we have to find out. So under initial condition 0, the two branches be segregated, one at the 0 input and at the 1 input. What happens? So when the input is 0, you get a output sequence of 0 0. Just write it here, 0 0. Okay, and next at the next level you are getting a 1. Okay, when the input is 1, at the initially what you are getting, the output is 1 1. Just write it here. Okay, fine. So next one, uh, that branch. Okay, that this branch. Okay, this branch, initial branch, is been subdivided into two sub branches. Okay, like we already said, it has to be divided into two based on zeros and one. Similarly, 0 and 1. What is his output? Okay, similarly at the bottom, 0 and 1. What is his output? So we have to find out. Okay, so how do you have to find out? So here, if you we have this 0. Okay, we have another pen here. Initially we have 0, and we have 0 here, and we have 0. Okay, and similarly we have 1 here, 0 here, 1 here. Okay, the highlighted region. So we need to find out what is this uh, second that is the second branch output. Okay, so we need to what we have to do is we need to go back and trace the required input digits. Okay, for example, first one is 0, second one is 0, and third one is 0. Okay, 0 0 0, we get what is the output 0 0. Then you have to write here. Okay. Similarly, you have a trace from this side. Okay, number 1, number 2, number 3. Okay, so 1 0 0. Okay, so 1 0 0, you have 1 1. You must go and see the lookup table. What is output? 1 1. Write it here. Okay, similarly at the bottom of the tree, you have 0 1 0. What is 0 1 0 is 1 0. So write it at the output. Okay, so similarly 1 1 0. So 1 1 0, you have 0 1. Okay, so write it here and the output. So in this way you have to build a code tree, like a generalized code tree. So you got the input for the input sequence, you got the output sequence for up to this tree. Okay, right. Similarly, you have to make a branch of it. Okay, you have to branch of it 0 1 1 0 1 1. You have to have a sub branch of it. Okay, and you have to write 0 1 0 1 0 1, and you have to trace back. It is 1 0. There is first one, second one, and third one. Tracing back is 0 0 0. You have 0 0. Similarly, 1 0 0. We have an output of 1 1. Similarly, at the bottom we have 1 2. Okay, tracing back 0 1 0. 0 1 0, you have 1 0. Okay, similarly you should write the output sequence for all the poetry output. Okay, so at last you will have this final version zeros and 1. Okay, and this up to this the code tree will be finalized. Okay, so from this, how we are going to take the generalized code tree. Okay, how we are going to find the generalized code tree is nothing but from the encoded sequence we are going to see. We are going to put a branch. Okay, so let us take the message bit. Okay, let us take the message bit. Okay, initially it will be 0. We start from here initially at 0. Next we have to decide which branch we have to go. Okay, see the input bit. Okay, and compare with the message bit. Okay, so initially 0, so next message bit will be 1, right? So you have to see the input which is 1 here, so it lies here. So this branch you can select. Next one you have to decide which is the incoming message bit. Next one is also 1. Okay, so you can choose this 1. Okay, next one the input message is 0. Okay, choose this part 0. Next one message bit is 1, last one, choose the path 1. Okay, in such a way we can able to trace the uh, path. Okay, trace the path according to the message bit. In this way you can able to trace a systematic path in a code tree. Okay, so from that we can able to get the output sequence 0 0 0 1 0 1 1 1 and 0. Okay, so this is a generalized code tree. So next one, what is a state diagram? Okay, so what the state diagram representation gives you from the tree. Okay, from the encoded sequence you have found out the code tree. Okay, these all is mainly used for the encoding process. So for encoding, we are going to see this what is encoded bit. Okay, So this is how we can able to trace and control. Or else we can able to use concept called state diagram. Okay, since already we have seen the types of encoding, that code tree, state diagram, and trellis. So the next third second one is the state diagram. So here the same thing, you get the same message bit here. Okay, the three shift registers, the same data for the same data which is given. Okay, you are going to plot this data. So what, how you are going to plot this? Like you are going to put a box, and inside the box you are going to put the possibility state. Okay, 0 0 0 1 1 0 1 1. 0 0 is taken into A, 0 1 is B, 1 0 is C, and 1 1 is D. These are the four states available. Okay, this one, okay, this section can be taken as a lower state. This section can be taken as the intermediate state, and this section can be taken as the higher state. Okay, so there are three levels: lower level, intermediate level, higher level. So we can able to divide like this, and we will solve it. One rule has to be followed. Rule number, if it is 0, move downward or same level. Okay, if it is 1, move upward or same level. If it is same level, you have to put the arrow mark. Okay, it is going to the same state. Okay, if it is, if you move upward, it should go to the some other upper state. Okay, some other upper state. Or move downward, you have to move from upward to downward to the lower state. This is the rule. So in this way, we are going to plot it from the encoded sequence. So 0 0. Let us take. Okay. So we got a sequence of 0 as a message input, 0 0. Okay. If you take the first level, okay, for the 0, you get a state of 0 0, which is up to the same level. Okay, it is going to the same level. 0 0 is same A. Okay, so you have to put the uh, level. You can see here this the arrow mark, which is going to the same A. Okay, so next one, when when the input is 1, it is second level, it is 1. So you have to you have each state will have, you can able to design it based on input is 0 or input is 1. Okay, so when an input is 0, it is giving the output as 0 0. It's with the same level. When the input is 1, it is going to the state B. Okay, it is going to the state B. Okay, so you can see this computation process from the previous. Okay, how it is being going from the code tree. Okay, it is going to the state of B with 1 1. Right, from this you can able to write the state diagram. So it is going to state B of output 1 1. So we should go from A to B, right? So you have to move from A to B. Okay, moving upward. Okay, so moving upward is 1. Okay, we have to put 1 here. Okay, at the output of 1 1. Okay, so either way you can also we can also move from A to C, right? Why we are moving from A to B? Because on the code tree it is on the second shift you can see that is B of 1 1. Okay, so either or every state will have two level possibilities of either 0 and 1. Okay, it's going to so at the 1 you have to move upward, and it's going to B. So this is over. Let us go to the B. Okay, so at the B 0 1. Okay, so what happens is, like when the input is 0. Okay, when the input is 0, so it is going to the same state. It's going to the same state. So we can able to see here, it is we can be go to the same state. Okay, so when it's going to same state, you cannot draw like this at the intermediate level. Okay, so At the intermediate level, there are two blocks. So either it will go to the same level. These two are the same level. So B to C or C to B. Okay. So compared to this lower level and the higher level, at the intermediate level, if it is the same level, it will be co-joining with B and C column. So 0, we have 1 0 here. Okay. So at the output 1 0, it is going to C. Similarly, for the B, okay, for the B, if it is going to be 1, okay, if it is going to be 1, it goes move upward. Okay, it is going to the section D with 0 1 as the output. Okay, so this blue line determines the same level, this red lines determines the different level. Okay, either upward or downward. So it is going to the upward. Similarly, go for C. C is having when we have a decision of 0. When you have a decision of 0, you can see here this C, from this it is going either it is going to this same level or at a different level. Okay, so at the 0 is going to the level move downward 0, this line, okay, with 1 1, and it is having a same level with respect to the 1, okay, here with the 0 0. So similarly, when you take the D, okay, when the input is 0, okay, it is moving downward with the output 0 1, and when the input is 1, it is having an output of 1 0, which is the same level. So the same level determines the this lower and higher level. It will be arrowed to itself, but on the intermediate section it will go to the adjacent level, the same level. Okay, by this way the state diagram has been we can able to draw the state diagram depending upon the number of states. So in this problem we have a number of states 4. So we have taken the 4 states. These are the 4 states A, B, C, D. The 4 to 0 0 0 1 1 0 1 1, and we have computed is output sequence with respect to the if input is 0, input is 1. Okay, so likewise you can able to trace the trace chart which you have done on the previous convolution tree. We can also able to trace using the state diagram. This is one part. Next one, trellis diagram. So from the state diagram, we can able to trace the trellis diagram. Okay. So in this trellis diagram, let us take the same sequence bit 1011 message bit. You have shift register, 3 shift register. Okay, encoded sequence can be taken x1 x2 x1 x2 x1 x2. So same thing, we are going to draw this trellis diagram. So this is mainly used to find out the encoded sequence. Okay, the proper encoded sequence which may have an error. So it can be also used for the decision making process for shortest route. Okay, there is a algorithm called shortest route algorithm. You can able to trace a shortest route from this trellis diagram. Okay, so this state diagram we have already done. So from that, what I going to do is we take 4 different states A, B, C, D, put a dotted line. Okay, put a dot next slightly, and we are going to put specific dots at certain distance. Okay, and we are going to join those dots. Okay, with respect to different encoded sequences. So I will repeat once again. So you're going to take A, B, C, D, okay, as a states. From that state, we are going to draw a release diagram, okay, based on the input and the output. So input may be like 0 and 1. Let us take, because we are analyzing it. If the input is 0, what is its output? If the input is 1, what is its output? So let us initially take, let me draw this line like this. at this point. Initially start from A, 0 input, 0 0, it goes straight, there is no deviation. Okay, it goes straight because it is it is on the same level. Okay, if it is on the same level, you have to go straight. Okay, if it is a different level, you go to that respective level. Okay, either B, C, or D. So next one, if it is 1, okay, if it is 1, what happens is goes to the level B. You can see from this diagram, it is going to the level B with the output 1 1. So it is, you have to draw like this, you have to go to the state B. Okay, put like this arrow mark, and for the 1, and we have an output of 1 1. Okay, so likewise you need to draw the first stage of sequence. Okay, second. Similarly, what happens to the second level when you find out the B? Okay, this A will be repeated exactly. A will be repeated exactly. There is no deviation. Okay, the deviation comes from the point B. Okay, so you have finished this, and you have to finish the next segment. So here, when B is 0 and 1, what happens? When B is 0, okay, it goes to the C. It goes to C point. This is the C line, right? You have to draw like this. And when the input is 0, you get output 1 0. Okay, from the state diagram. Similarly, when the B is 1, it is going to D. Okay, so you have to draw an arrow mark which is focusing to the D point, where you can write input is 1 and 0 1. Right? Right. So we have framed the first segment and the second segment. So uh, third one. Okay, we have to go for the third region. So for that, just copy and paste all these three what you've done on the previous. It is like clumsy over there on the icon. But what you have to do is, what's the computation you would like to focus on this. We have followed A, B. Next one is the C. We have to focus on C. So when C is 0, okay, it is going to A. Okay, you can see here it is going to A point with the 0 and 1 point. Okay, similarly when C is equal to 1, it is going to B. Okay, with the sequence of input 1 and the output of 0 0. Okay, so from this you have to copy all this ABC sequence corresponding to the next last sequence D, and you have to find out from D where it is going. When it is going like when D is 0, okay, it goes to the same region. Okay, you can see here it goes to the same. Right. Similarly, when D is equal to 1, D1 is goes to the C. Okay, it goes to the C of, okay, 1. Okay, is it sequence of 1. Sorry, when D is equal to 1, it is going to the having the same sequence. Okay, and D is equal to 0. Okay, it's having going to C at a output sequence of 0 1. Right. So this is where the viterbi, this the trellis diagram has been framed. Okay, so from the state diagram we can able to converge to the viterbi, that is like a trellis diagram. So previously I like to show, we start from code tree. Okay, code tree, we have generalized code tree. From the generalized code tree we have framed the state diagram. From the state diagram we have framed the trellis diagram. Okay, so I repeat once again, these are the 4 state. A, B, C, D are the 4 state. This will be decided based on the, okay, number of shift registers, and let us take 0 0 0 1 1 0 1 1 for the different states, and for the different state you give an input of 0 or 1. What is his output? Okay, that is already been computed. Okay, and it is been we have traced the state diagram. From the state diagram we are converging to the trellis diagram. Right. So the list diagram, what is in fact once you done on the previous, just copy and paste on the second. Okay. Likewise, initially copy and paste on the previous three, previously on the next state, and we copy the previous state and paste on the next. So that's the way we have to compute it and find out the new state. So basics of viterbi algorithm. So we'll be seeing the concept of viterbi. So it comes under the decoding process. So it's a method of decoding convolution code. So previously we saw the encoding process, and now we are going to shift into decoding process. It is the method of decoding convolution code. It is used trellis decoder to decode received data. So it uses a trellis diagram. Okay. So it uses a trellis diagram to decode the received data. So this computation is more important for the decoding process. Objective is nothing but to find the best path to the trellis that is closest to the received data sequence. That's the thing. The best path to the trellis. You need to trace a path from this trellis diagram. You need to trace any path. Okay, such a way it is the best path with a less handling distance. Okay, it is somewhat closer to the received data sequence. See, in this code, you receive some code, right, in the receiver. That receiver, you need to find out error free or not. Okay, for that, you need to draw the status representation and find out whether received data sequence matched with the code word, okay, error code word sequence. So that's the final sequence. So when it is matched, okay, or else I can say zero error, you can directly upload into a sheet or upload or you can transmit in a wire or transmit to the receiver. Okay, you can give it a decision maker. So before the decision maker, these are things are available. So following steps to be solved to solve literally algorithm. Okay, so some things we have to make sure uh, this has been followed. Number one, make release encoder. Number two, from the release encoder, make release diagram. So number three, match weighting with respect to release diagram. Okay, you have to add some weight to this each and every release diagram. And next one, you find the minimum weight part on release. You have to add some weight. From that weight, you need to find out the minimum weight. Okay, that is it. That is the path of the or the best path of the through the release diagram. That best path will give the closest approximation to the received data sequence. Okay. So example, let us take. So example, let us take step one, release encoder. M0, M1 input. Let us take three shift registers. We have encoders, two adders. We got two sequence x1 and x2. These are all we have seen. Okay. So if the M0 is the M0 and M1 are the shift registers, M2 is the received message input. Okay, 0 1 0 1 0 1 0 1. Okay, with respect to different message sequence, what is your M0 and M1 shifting? That's the thing. Okay, so what happens here is like you have to represent the flow state here 0 0 0 1 1 0 1 1. Initially, for the input 0, you have 0 0. If it is 1, if it is 1, you get 1 1. Okay, when it is 1, you get 1 1. Okay, so this trellis diagram we have to we have already been seen. Okay, and the previous trellis mode. Just an example of viterbi algorithm how this trellis diagram is used to find out the shortest path. Similarly, it has been copied and it has been pasted here. Okay, similarly, we have to find out the B node. Okay, under a condition of 0 and 1. What is happening when it is 0 and 1? Okay, you get output sequence as 1 0 and 1 1. Okay, so at the 0, it is going to the C. Okay, it is going to the C is 1 0. Okay, 1 0. So you have to see for the input message what is this sequence. Okay, M1 and M2. So 1 0 and 1 1. For the input of 1, okay, it is going to 1 0. So 1 0 is nothing but C. Okay, next one for the input of 1, it is going to the state 1 1. Okay, or else I can say on the next diagram for the for the input, for example, the C 0, it is going to 0 0. Okay, 0 0 is A, right? Or under the input of 1, it is going to the 0 1. 0 1 is nothing but B. So I'll show on the nested diagram. Okay. You can see on the C section this node. Okay, 0 0. Okay, it is going to 0 1 B. So from this tabulation, okay, we can able to find out where that particular node under condition at the input of 0 or 1 is gone. So we have segregated each and everything as A, B, C, D. Okay. So for that, what is his output? Output is these are the x1 and x2 of the output. Right? So you can able to compute by using this state table. Okay, where you have the x1 x2 output, m2 is the input message bit, m0 and m1 are the state shift registers. Okay, so we can able to compute a trellis diagram like this. It will be like very costly at the last state. You can see it is very much scribbled out, but nothing but the previously it has been copied and pasted here, and we are doing the computation on the D. Okay, so let us do the D side. Let us take this D. Okay, for an input of 0, it is going to 0 1 0. Okay, 1 0 is C. Okay, it is having a weight, it is getting an output of 0 1. You have to add that. Or next one, when the input is 1, it is going to 1 1. Okay, 1 1 is D, same level. Okay, same level, and it is having an output of 1 0 1 0. Fine. So this is the overall receive release diagram. How do you put the weight? So already I told you that you have to follow the make release encoder. From the release encoder, make release diagram. Okay. So we have step one. We have made a release encoder tabulation. Okay, with respect to different sequence. Okay. So from that sequence, we have framed the release diagram. This is release diagram. Okay, from this release diagram, you have to add weight. This 1, 2 are the weighting functions. Okay, how do you add weight? Fine. So here you need to take the receive sequence. Okay, what's the receive sequence? 0 0 0 1 1 0 0 1. We have a lot of sequence, right? So you have to write in that respective two different notation. Okay, 0 1. Okay, 1 0 1 0 0 0 0. Okay. So you need to write that sequence uh, on the top, okay, and you need to compare with the bottom. Okay, you need to compare with the bottom levels. Okay, so you need to add a modulo addition. Okay, let us take this segment. So you got a receive sequence data. Here it is already given 0 1 1 0 1 1 0 0. So from that you can able to segregate into two bit. That 1 1 bit you can able to add on the first one, second one, okay, third one, fourth one, fifth one. Right? So you need to compare with the value which is given here 0 0 1 1. Okay, that 0 0 1 1 is nothing but your output sequence. This output sequence. Okay, encoded sequence. You need to compare the received data bit with the encoded sequence. I'm sure you might have understood. So 0 0 0 1. What's the difference? How much difference you have that after you put modulo to add? Okay, you have 1. Okay, 0 0. We have one different sequence here, 1 0. So the minimum Hamming distance you have to put as 1 here. Okay, 1. Next one, you compare with the 0 1 with the 1 1. Okay, you have difference in bit like 1. Okay, put here 1. Next one, you compare with 1 0 with the 0 0 1 1 1 0 0 1. Okay, if you compare it, you get these terms. You see here, uh, you get here 1 0 0 0, right? So you need to put you have how much you have, one. Okay, you should get one, but you need to add with the previous weight. Okay, 1 plus 1 2. Also, if you go on next state, you need to add at the previous weight. So if you compare 1 0 with 1 1, okay, you get difference is 1. Okay, modulo to addition, you have 1 1 0 0 1, you get 1. Okay, you have 1, and already you have 1 here. Add it and put it here 2. And similarly, if you add 1 0 1 0, you have 1, but it doesn't have any weighting function here. So you just put the exact value here. Okay, the next one, 1 0 0 1, last one. So from this, we can able to compare this sequence and this one. We have uh, 3. Okay, so you need to compare. You need to compare basically with the prefixed where your nodal points come. So we cannot compare with this node point with this node point because there is no weighting function here. You need to compare this with this weighting function. Okay, so if you take 1 0 and 0 1, the difference you get is 2 2, right? 2 plus previous weight is 1. 2 plus 1 3. In such a way you need to compute the weighting function. So once again I will tell you, is 1 0 is there. Okay, there is 1 0 here. Okay, the difference, if you see here, it is a 0 0, cancelled out. Okay, 1 1 cancelled out, you have 0 here. That 0 will be added with the previous weighting function 1, so you get 1 here. Okay, similarly this 1 1 will be compared with the 0 1, so you have difference is 2. Okay, add with the previous where your nodal weight. Okay, previous nodal weight 1. Okay, you get 3. So this is where the weight will added. So next one, similarly if you going to add, okay, if you're going to add with 1 1, okay, 1 1 with the 0 0, so difference is 2, right? So 2 2 plus 2, previously you get 4, right? You get 4. Similarly you need to add this 1 1 with the 1 0, but you see here, this node, okay, this node receives two different, okay, one different, he receives two paths. One path is here and another path is from this node. Can you able to see? Okay, so previously one is transmitting, one is receiving. Okay, here at this point there's something different. One node receive two, okay, two paths. So what happens here is like you receive two different weightings. So with respect to the path 1, you get 4. With respect to this path, okay, to this path, 1 1 plus 1 1, you get 0 0 plus this added function is 1. Okay, so either you are getting two functions. One is 4 at the path 1, okay, at the path 1, this from this node, and 1 from this node, which we have to select. It's a general rule like you take the minimum value. Okay, you take the minimum value because at most we are going to trace based on the minimum value. So negotiate this 4. Okay, if you take away this 4 weighting, you have to see that which line this 4 has been computed. Okay, this is based from this node, right? So you have to delete this path. You have to delete this path. Okay, else you cannot use this path. Fine. So this one has been governed only from this node. So this path is being terminated. Okay. So Similarly, you have to find out for the previous next nodes. Okay, if you see this, you have two different conditions. Okay, one is 3 and 2. You take away this 3. Okay, and use this 2 where you have to find out where this 3 weightages come. That link will be terminated. Okay, it will be terminated. So by computing all the nodes, okay, if you compute all these nodes, you have lots of weights being available. Okay, you get lot of weighting functions. From that, you have to trace the last step, match with respect to the list diagram, match weights which is having a less weighted value. Okay, so you start from the starting node. Okay, you start from the starting node. Okay, so from there, what you're going to do is you're going to trace. Okay, the lowest possible uh, node. Well, so either you can go by like this. Okay, if you go by like this, you'll be having two decisions, one or two, which is the highest weighting function, right? We need to have low. By going by this way, the next preceding nodes will be like my 3 or 1. I can go by 3, right? So I can use this tracing, this path as the best fit path for my receive sequence. Okay. So by you can go to this node 1. Okay, as I already said that some nodes some links are terminated. You have to put the cross for that, for the links being terminated. Because you cannot go by that link. From this, you have to decide which way you can go. Like you have two decisions: one is two, and one is one. I can go by two, right? Minimum Hamming distance. So next one is I have this value. If you compare with 0, 0, 1, 1, literally you will get the highest greater than 2. These are all greater than 2. If you can complete by yourself, it will be all greater than 2. So you can choose this one line. Okay, one line from this I have 2 or 1. I can choose one. By this way, you can able to compute the uh, minimum weighting function based from the trellis diagram. Okay, so this is what the thing final version. Okay, final trace line. From this trace line, the decoded data sequence is given as, okay. Let us find the decoded data sequence: 1 1 10 11 00 00. Can you understand? So we got the decoded data sequence. You see the received data sequence. Okay? When you compare the data sequence decoded and the received data sequence, there is a small error here. Okay, you see the 0 here, there's a 1 here. There is a bit being changed. Remaining all bits are same. By this way, you can able to at this time you can able to decode the received data sequence. From the decoded data sequence, we can able to have a error correction. Okay, so this convolution encoding, this is the same thing which I have said on the previous slide. You need to find the survivor path having uh, least Hamming distance. That's the main thing. Okay, least Hamming distance. So you have to find out the least Hamming distance. That's a survivor path. Okay, so that's a survivor path that can be taken as a decoded data sequence. Okay, so I'm sure this class is over. Um, Next class, we will see the concept of sequential decoding. Okay, so do you have any doubt?